Hello calculus students, here we are with 11.2, trig functions differentiation, where we take the derivative of the sine and cosine and all the other trig functions. So, the derivative of the sine and cosine. The derivative of the sine of x is cosine x, and the derivative of the cosine x is negative sine x. Let me try and convince you of this with a little red-green proof here. Remember the red-green show? Let's look at the increasing, decreasing. We actually had this on an exercise in the second quarter review packet. You're increasing here, then decreasing, still decreasing, and then increasing. So the derivative should be positive, then negative, then positive. Now in terms of the green part, and also right here we have a max, right at pi over 2. So the derivative will be 0 there. And also at 3 pi over 2, we have a min, so the derivative will be 0 there. In terms of the green part of the show, this is concave down the whole time, so we're decreasing. Concave up, increasing. And here we have an inflection point, and this ends up being a point of most increase, decrease. And if you look at this, it looks like these inflection points have slopes of 1 and negative 1. 1 here, negative 1 down here, and 1 here at the end of the cycle. And you see we end up getting something that looks like the cosine. So for y equals sine x, the derivative is cosine x. Now the proof involves something that we haven't reviewed in trig, and that involves the sign of addition and so forth. But here's our limit definition of the derivative. Notice how the sine of x plus delta x gets split up into this trig addition formula. And by carefully rearranging things, we use our trig limits we just talked about, sine h over h here, cosine 1 minus cosine delta x over x. And that's 0, and this limit's 1, and so the thing ends up being cosine x. Notice when you take the derivative of the cosine, though, you don't go back to the sine, because the cosine starts at the maximum, so you get zeros, 0 here, 0 here, but here you start by decreasing, so you actually end up being negative first. So you get the exact opposite of the sine for the derivative of the cosine. And here's some examples here. 3 sine x, the derivative is 3 cosine x. Sine x over 2, think of that as 1/2 times sine x, so this is the constant multiplier rule being used here. X plus cosine x, the derivative of x is 1, and the derivative of cosine x is negative sine x. Let's try something that's a little more complicated involving the product rule here now. For the derivative, y prime, we have to use the product rule in this part, so we'll take 2x times the derivative of the cosine, which is negative sine, plus, now we'll take the derivative of the 2x, which is 2, and then leave the cosine of x alone. That was the product rule on that part. Notice you don't need the product rule on this part because it's a constant multiplier, and minus 2 times the derivative of the sine, which is the cosine. So you get negative 2x sine x plus 2 cosine x minus 2 cosine x. Those cancel, and so we just get negative 2x sine x. And again, you get your calculator to help check. Let's do the check. Oops, see now what happened there. I think I added a page. Not scrolling over here. Oh, I put it in the wrong spot. So sorry. Let's just take this one out. Put one in after this here. So here's the check on the TI-89. D 2x cosine x minus 2 sine x with respect to x. And let's see what it says. And I suspected you do have to put a little multiplication symbol in here because it gets confused with what x cosine x is. It thinks it's a variable. But it does take out to be negative 2x sine x. Check. Now, here's some examples using the derivative to find the slope of the curve at a given point. Find the slope of the graph of f(x) equals 2 cosine x at the following points. Well, the derivative is 2 times negative sine x, or that's negative 2 sine x. And we end up with, let's see what happens at these different points here. We just have to put them in the negative 2 sine x. So for part A here, it'll be negative 2 times the sine of negative pi over 2. And on the unit circle, negative pi over 2 is down here. The sine is negative 1, so this ends up being 2. For pi over 3, the sine of pi over 3 is square root of 3 over 2, but we're multiplying by negative 2, so we get negative square root of 3. And for pi over 2, the sine of pi is 0, so you just get 0 for that. And if you look at a graph of 2 cosine x, which looks something like this, up to 2 and down to negative 2, at negative pi over 2 comma 0, when you're back here, you have this intense slope of 2. At pi over 3 comma 1, right around here, you've got a decreasing slope. And at pi comma negative 2, you've got a horizontal slope. All checks out. Here are the other trig functions now. The derivative of the tangent is the secant squared. Now that's strange. The derivative of the secant is secant tangent. The derivative of the cotangent is negative cosecant. Notice it's just like the tangent, but you got a negative sign here. And the derivative of the cosecant of x is negative cosecant x, cotangent x. So maybe you noticed a pattern here. The derivative with respect to x of the sine of x is just plain old cosine. When you take the derivative with respect to x of the cosine of x, you get negative sine of x. So notice whenever you take a derivative of a co-function, you end up with this negative factor in front. It's a good idea to memorize these, but these are something you can include on your formula sheet. And here's why the tangent ends up being so strange. You have to apply the quotient rule to it. Think of it as sine over cosine. So low d high minus high d low over low squared. And use a trig identity, cosine squared plus sine squared to get 1. And that's how you get secant squared of x. So here's differentiating with some trig functions here. Derivative of x is just 1. Derivative of tangent is secant squared. Here you've got x, secant x. You have to use the product rule, so we leave the x alone, take the derivative of the secant. And remember, the secant is kind of complicated. You get the derivative of secant tangent plus secant x times 1. And that's the product rule. And then they went ahead and factored out secant x there. Now, different forms of the derivative. We're going to take the derivative in both these forms. We should get the same answer, but it might look a little different here. If we look at 1 minus cosine x over sine of x and just leave it like that, now we have to use the quotient rule. We do the derivative. And so we get low d high, so the bottom, times the derivative of the top, which would be 0. Remember, the derivative of the cosine is negative sine. Minus high, which is minus cosine x, times the derivative of the bottom, which is derivative of the sine is cosine x, all over the bottom squared. So I'm getting sine times 0 minus 0, that makes sine squared x, plus, or minus cosine x, plus cosine squared x, over sine squared x. And so we get sine squared plus cosine squared is 1 minus cosine x all over sine squared x. Now, I'm actually going to take another step here because I see there's a way I could maybe simplify this because I've got 1 minus cosine x. Sine squared is 1 minus cosine squared x. And 1 minus cosine squared x can factor into a difference times a sum. And I just think this looks simpler because it's got the fewest number of functions in it for our derivative. I'm just going to take a second here to see what the calculator thinks it should be, see if it actually went through this extra step. So the TI-89 check. D, 1 minus cos x, get that in parentheses, divided by sine x with respect to x. Let's see what it says. So this is interesting. The calculator came up with this answer, negative cosine x minus 1 over sine squared x. So it's actually sort of agreeing with the answer we stopped at up here. So I'd accept this. I'd accept this. Both those are fine. Realize, though, there might be a lot of different forms of final answer that other people would consider simplified. Especially now if we took the step of changing this first. Now, see how they took 1 divided by sine. To get to this step, they did 1 over sine x minus cosine x over sine x to create 1 over sine is cosecant and cosine over sine is cotangent squared. It is cotangent. So let's try taking that derivative. If we look at this as y equals the original function as, I believe it was cosecant x minus cotangent x. Cosecant x minus cotangent x. You get a very different derivative now if we just use the derivative rule on cosecant. Remember, that's negative cosecant cotangent minus, and the derivative of the cotangent is negative cosecant squared. Negative cosecant squared of x. Let me erase that. So we end up with negative cosecant x cotangent x plus cosecant squared of x. Now, how is that the same as the other answers? And cosecant cotangent doesn't really simplify. But we could factor out, so I'd accept this as an answer. But let's make sure it's equivalent to the ones we came up with over here. Because we could factor out a cosecant. And then it becomes negative cotangent x plus cosecant x. And now to see how it's equivalent to the sine and cosine form, let's change everything to sine and cosine. So this is 1 over sine x. Cotangent is minus cosine x over sine x. Cosecant x is 1 over sine x. And sure enough, you've got a least common denominator, you have sine x here, so it's negative cosine x plus 1 over sine x times 1 over sine x. And we get negative cosine x plus 1 over sine squared x, which agrees with the answer we had way over here. Okay? So, here's the derivatives of the trig functions now with the u notation. Remind you to take the derivative of the inner function. So keep that in mind now when we do things like sine 2x. The derivative of the sine is the cosine, but then you also have to multiply by the derivative of the inner function. That's where that 2 comes from. Here the derivative of the cosine is negative sine. U equals x minus 1. The derivative of u, du, just equals dx. Right? The derivative of x minus 1 is just 1, so that's why there's nothing left over on that one. Y equals tan e to the x, so you take the derivative of the tan, which is secant squared of e to the x, but notice this e to the x comes from the derivative of the inner function. So let's try a few of these more. Oh, here's some more involving parentheses. Notice all these look very similar. But in this case, by cosine 3x squared, we imply that all of it's inside the cosine. Cosine of 3 times x squared is just a constant multiplier on the x squared. Cosine of 3x quantity squared, notice you're squaring this, so you have 9x squared on the inside. And cosine squared of 3x, this is the one I really want to focus on. Because this notation of squaring the word cosine actually means the cosine of 3x quantity squared. So all of cosine 3x becomes your inner function. So twice, leave the inner function alone, and now raise it to the first power, so it's just like that. Now take the derivative of cosine 3x, which is negative sine 3x, and then you also have to take the derivative of the inner function of that. So this one's very tricky because it's got 3 levels of nesting here. There's the squaring function, there's the cosine function, and there's the tripling function. Let's try this with another composite function here. Differentiates f of t equals the square root of the sine of 4t. So we can think of this as sine of 4t all raised to the 1/2 power. So here's another example where you have 3 different levels of composition. So let's start with the first level. That is just dealing with the derivative of the outermost function. That's the 1/2 power. So that's 1/2 yada yada to the negative 1/2. I said yada yada because the intention is to leave this inner function alone now. I'm going to shift to another color to help me remember to take the derivative of that next innermost function. And that would be, the derivative of the sine is the cosine. But I also have an inner function there, and that one is 4t. And we got to take the derivative of that function as well. And the derivative of that is 4. So it all boils down, we've got 4 times 1/2, so that's 2, cosine 4t. And let's put all this sine in the bottom as the square root of sine of 4t, because it's raised to the negative 1/2 now. Okay? Let's see what sort of twisted, bizarre form the calculator says. That for the ti and I check, you should go derivative of, now getting this all in here like this, we'll have to use parentheses, sine, parentheses, 4t, and parentheses raised to the 0.5 with respect to t. And let's see what the calculator says. calculator agrees exactly. Check. Now, implicit differentiation. I did one of these examples because I put a big emphasis on this in the rest of our sections. And so I took one from the homework 76. X equals the secant of 1 over y. X equals the secant of 1 over y. And we're going to take the derivative of both sides with respect to x. With respect to x is the secant of 1 over y. So the derivative with respect to x of x is just 1. The derivative of the secant is secant tangent. So you get secant 1 over y, tangent 1 over y. But then we also have to come up with the derivative of the inner function. And the derivative of y to the negative 1 here is going to be negative 1 y to the negative 2 dy dx from the chain rule. And I take a little more time on this just to solve it for dy dx. So we have dy dx, well, 1 over secant 1 over y, tangent 1 over y. And let's see, this is y to the negative 2, so it'll be y to the positive 2 on the other side, and we have a negative associated with that, equals dy dx. And do you remember the reciprocal of the secant? Secant is 1 over cosine, so basically we're getting cosine 1 over y. Reciprocal of the tangent is cotangent 1 over y times y squared, and we have a negative there. Let's see what the calculator says. Now for the calculator check, we go imp diff, and then put in the whole equation, x equals secant, and that secant's in your catalog. It's not on your front screen, but it's on your catalog. Left parentheses 1 divided by y with respect to x, and then you also have to tell it the dependent variable. Okay, so the calculator gave me negative cosine of 1 over y, all that quantity squared, y squared over the sine of 1 over y. Do you see how these are the same? Because you could take my answer, change cotangent to cosine over sine, and so that's how they're getting cosine squared of 1 over y, and that's sine 1 over y in the bottom. I'd accept either. Okay. Flange out.